We'll survive. So we're going to take a look at energy as a topic. And this is going to be the first time we're going to explicitly look at one of the main pillars of all of physics. And that's the conservation laws. I'll bring this down for you, sir. Most of physics is built on the back of conservation. Oh my God. There we go. Yes. Okay. Now this definition and technically this law is a little bit outdated by like 115 years. But for us right now, it's not bad. It's okay. Conservation of energy tells us that the total amount of energy that exists in the universe stays roughly, more or less, the same. I'm confident that most of us have heard energy cannot be created or destroyed, right? That's not a bad picture of conservation of energy, and it was actually the whole picture of conservation of energy for a really long time, really long time. As a quantity, as a fundamental idea, the amount of energy in the universe doesn't really change by that much at any given moment. It really doesn't. But Einstein came around and figured out that energy and matter, physical, actual matter, are really just different forms of the same thing. Kind of like how ice cubes and liquid ice, liquid water, which is liquid ice, whatever, are two different forms of the same thing. They're both H2O, just in different ways. And he figured out that if I take a whole bunch of energy and I squeeze it together, I will create matter. I will pop out some type of particle. And that actually happens all of the time. If you bring your arms or your hands close like this, in that space, there are billions and billions and billions of tiny particles that are just spontaneously being created. They're little pockets of heat sporadically spread out in that area that kind of coalesce together and make a particle. Pops out. And then somewhere else, a particle kind of breaks apart and creates heat, turns into energy. And that stuff kind of happens everywhere in the universe. But we don't care. We really don't. We don't care too much about when we take energy and turn it into matter, or when we take matter and turn it into energy. By the way, that's the whole idea behind the nuclear bomb, right? Or nuclear energy as a whole. If I take matter and I break it apart, the act of breaking it apart releases way more energy in those bonds than what would need to be put in to break it. Do you get what I'm saying? Like I need to put a certain amount of energy to break something, right? I need to put effort to break it. But when I break apart matter, like fundamental particles, the energy that I get out is actually way more than the energy needed to break it apart. It's weird. It's really weird. It's one of those crazy things in science. It is. Okay. Energy by itself would not be. But then if I take into account the fact that some of the matter is turning into energy, then as a whole, yes, it is. But we're not going to look at those cases. We're really going to look at cases where energy stays in energy form. It doesn't turn into matter, and matter isn't going to turn into energy. It's not just going to poof, happen. Yeah.
Maybe I don't have a clear definition of what matter is, but are you saying that something that was an atom of something is no longer...
Or a particle, like a proton. Like if I had a flying proton in space, it could dissolve or break apart into energy, into some type of kinetic or thermal or potential, not potential, but some type of other type of energy. Or more likely that usually happens is I'll get energy that gets close together in a close proximity. I get a collection of energy really close, and then they'll condense and then turn into a pion or a muon or an electron. Like it'll turn into a smaller particle. It just happens. It happens. And the more energy that you get close together, the bigger the particle you could make. It's funky. That stuff blew my mind. Like I'd never... And if you think about Einstein's E equals mc squared, what he's saying there is if I have a certain amount of mass, Just any particle, anything of mass, it has an energy associated with it. And if it's not doing anything, if it's at rest, like that chair, then the amount of energy that it has is mc squared. If it's not at rest, it's no longer mc squared. It's gamma mc squared. But whatever, doesn't matter.
You said the amount of energy in the universe is always the same, pretty much.
Yeah,
So
for
like,
us,
isn't the
more or
universe
less.
like expanding or something?
It's crazy how that do that, right?
Yeah, how does it accelerate with no energy being added to it?
It's crazy how it do that, right?
Yeah.
Those are great questions.
No one.
Those are great questions. This is very unsatisfying to me. This is one of those things that makes me very uncomfortable and unhappy. Because the definition of energy really is the ability a system has to perform work, to do work. I could say that something has energy if that something could do work. And that makes me very unhappy because then that means I need to know what the heck work is. Great. That's a very unsatisfying definition. Okay, so we got to keep going and we got to define what work is. It's not a Rihanna song. And in our everyday lives, when we think of the word work, we normally, I don't know about you, I don't particularly think of Mike Rowe, but I do think about the things that Mike Rowe does on his show. I think about the things that I'm doing right now. I think about going to the gym. I think about working out, quote unquote. But none of those things are actually good definitions of work. Not in the physics sense, not in the scientific sense. One way that we can think about work is the ability to change the state of a system. Bless you. Something could have work if it has the ability to change. Or if it has been changed.
Is the word state?
It could change, I won't use a different word than state, form. So it could change from solid, liquid, gas. It could change where it is, right? It could change from being here to being here. It could change size. It could change anything about that system. That system is no longer the same as it was before. Something about it is now different. What? Anything. Could be anything. Anything that describes the thing could be different. Its color, its size, its shape, its speed, its mass, its position relative to something. Something about it has changed. It's no longer identical to what it was before. Yes.
So I'm confused. Is it the ability to change the state of the system or the act of changing it?
Okay. So if I think about work as being something about changes, well, what else do we know does changes? Forces is the act that I do to create changes. Okay? I apply a force, I do a force, right? On something. So, chair at rest. This displeases me for some reason, and the only way to change this system is for me to do a thing, which is apply a force. That's the only way to do it. Yeah. I have to apply a force. That's the act that I'm doing on the system. Now, when I perform this act, I'm giving the system, or, depending on how I do it, taking away from the system, work. It gains the ability for work. So the action that is done is force. That's the actual physical thing that I'm doing to this system. But then it gains this new thing called energy, it's called work, that describes how it was changed.
So it's kind of like a post.
It's kind of like an action-reaction type of thing.
Yeah.
I am doing work on the system, so you could say that this thing is getting the work that I have done on it. Think about it in terms of like money. Like I earned my $100, but if I want a service from you, I must give you that $100. Right? Who's gaining the $100? You are. I am the one that is giving the $100 away. I'm the one doing the moneying, but you are the one that is receiving the money. So I could be here doing the work, doing the force that is giving this thing work, but this is the recipient of that work. It is the one that is gaining that work. I can stay there for now.
But a system can have work without actually changing.
Keep that. Hold on. Hold on to that for 1 second.
Wait,
I think one slide.
The fact that the chair is on the table, doesn't it have work automatically because it like?
Well, I needed to do work to get it on the table.
Yeah,
So
no,
it
but I'm
has
saying
your
right
work.
now, if you push it off, right, it can fall and.
Yes, and then at that point, then we're getting into some stuff that's a little bit later on. If what is the thing that's going to make it fall?
A force. Or
Yeah.
gravity.
What? Gravity, the force of gravity. And at that point, we could say that the force of gravity is doing work on this thing to make it fall, to make it fall. So yeah, and then I needed to do work to get it from the tape, from the floor up on the table.
Yeah.
So work as a thing is related to forces, but related to individual forces, right? So a particular force does a particular work. Does that make sense?
So is there a law of conservation of work or force?
Well, work is an energy,
Yeah.
so it has to follow the same rules as conservation of energy in the grand scheme. We're going to get to that specifically at the end of this.
And both work and energy are
We're going to get to that in a second. In 2 slides. In two slides. Another definition for work, if you don't like the last one, I can expand on this a little bit. We did say it was the ability to change. But, what does that mean? Well, the changes could come from a mechanical transfer of energy, either into or out of a system by pushing or pulling. For the record, this is one thing. That's one thing. That's one place that work could come from. Now, one big thing to think about is, what is that? What is mechanical? We'll get to that in 1 second. What is mechanical? But works come from mechanical transfers of energy, which are pushes or pulls. That's what mechanical transfers come from, pushes or pulls. It also comes from heat. This is the second thing. Heat is an example of a non-mechanical transfer of energy. So work really encompasses mechanical changes of energy and non-mechanical changes of energy. Okay? So anybody want to take a guess at what the most obvious question is? Yeah, what is mechanical? Okay, well, a push or a pull is not a bad way of thinking about it. It is a push or a pull, more or less. But mechanical doesn't necessarily mean machine. So it's not like the wedge or the lever or the fulcrum. It's not really that. Mechanical really talks about changes in the physical state of the system. So I was here, and now I'm over here. I've changed my position. That would be a mechanical change. I've applied a force on my system to change where it is in space. Now, we know that if I change where I am, there's a bunch of other secondary and tertiary things that change as well. If I change my position, I had to move. If I moved, that means I had, starts with a V. Velocity. But then if I didn't have velocity and then I had velocity, my velocity changed, that means I had acceleration. So when I do those changes in position, in the back of my mind, we should keep the thought that that's also creating changes in velocities, getting changes in accelerations. It's getting changes in kinematics, really. Kinematics is a big thing there.
What about breaking something to get a punch of wood?
That's a little bit weirder. It's a little bit weirder because you got to define what your system is. You could think of it in terms of a position, like a particle, a point on the board that you're breaking is changing its position, so it's gaining speed, whatever. It was at rest, you hit it and broke it, it moved, so it gained kinetic energy. But we almost never really think about that. Usually those changes come from like a non-mechanical source where we had to break the bonds in between the particles. So it's not that we needed to move the particles, it's that we needed, heat is an umbrella term, to be fair. Like, it's not just getting hot, and it's not a great umbrella term. When I was in physics, the umbrella term we used was internal energy, but now the new hot thing is heat. I don't know why they decided to change, but it's just an umbrella term that means any change that's not actually like a change in physical position. It's any internal change, usually related to breaking bonds, creating bonds, or increasing, decreasing temperature. Those are like the three biggest places that you're going to see that heat.
So if you have
Yeah.
Wait, can you go back one second?
So we're going to get back to this idea of mechanical in a little bit, because we're going to separate our types of energies in terms of mechanical energies and not mechanical energies. And it's not super satisfying, but it is important.
Wait, where's the one that's 4 times distance?
Almost. We're a calculus class, so almost.
But, yeah.
Almost. Let's get rid of some of the details really quickly, because I don't think these are they're important, but they're not fundamental, and I just want to get rid of them so we can get to the real juicy stuff. The variable that we use for work is capital W. Please be careful between that and weight. We're not completely done with weight because, we already know there's a tie between work and force. Weight is a type of force. There's a very good chance that I could probably see weight again. I would recommend, instead of using W to represent weight, I would use either Fg or mg, just to make your life a little bit easier. Mass times gravity, which is weight.
Oh, you mean not
Yeah. Not m sub g. No.
Yeah,
Literally m times g.
Yeah.
The SI unit of work is the joule, for the record. This is also the same unit as energy, because work is energy. They're the same type of thing. Energy is the ability to have work, so they have to have the same energy. The same units. The joule is abbreviated as capital J. The American Standard System, I forgot, the United States Convention system for units uses the calorie. For the record, fun fact, if you take a look at if you take a look at the back of that thing, usually it's cal, C-A-L, with a lowercase c. That's a lie. They're kilocalories. It should be a capital C, but for some reason no one's ever called them out on it, and it doesn't really hurt anybody because we all know that, but whatever. 1 calorie is 4.184 joules. If you ever actually need it, I'll give it to you, but it's important to know that. Joules are usually bigger numbers. Now, energy and work is a scalar quantity. We're really just talking about amounts. That doesn't mean that they can't have signs. It's just that the signs don't talk about direction, right? Like up, down, left, right, forward, backwards. I don't know any other. Clockwise, counterclockwise. I don't have any other directions. Yeah, that's it. That's all I can think of. But the signs imply either a system is gaining energy, so a positive work, or it is losing energy. Think about it like your bank account. If you see a positive, like a plus 100, that means that you gained $100. If you see a minus 100, that means your bank account lost $100. Energy is very, very similar.
You can't say that it's gaining or losing energy, because energy was defined with works.
The system, so here's where you got to think about what it means to be a system.
Yeah.
The entire universe is a system. And the entire universe has a delta of 0. Can't change, can't gain or lose. That's not useful in the slightest when we actually do stuff. So we think more about smaller scale systems, right? So, for example, I could gain or lose energy.
Yeah.
I eat, I gain energy from the food that I have in my belly that gets broken down. That's me gaining energy. Does that mean the universe has gained or lost energy? No, because the energy that was in the food is now in me, and the universe, I'm still in the universe, so we're in the same place. Does that make sense? But my system didn't have the food before, has the food now, I've gained. Does that make sense? So when I'm talking about gaining or losing, I'm talking about energy going into a system or getting out of a system. The smaller scale system, not the universe system.
Yeah, but you're using that to define work? Or?
No, I'm just saying that when I have a positive work, my system is gaining energy. When I have a negative work, my system is losing energy. Here's where we're going to start with some calculus. Here's where things start to get a little bit fun. You'll recognize some of these things as coming from your book because the writing was really good. I really enjoyed the way they wrote it. So. When I say that work is done on something, that means that it needed to have changed. That means that the system needed to have moved from one place to another. It needed to have displaced. Since we're in a calculus class, we can have variable functions. Does that make sense? Right? Like in an algebra class, a variable force function is really difficult to deal with because it's a vector. And there is no good tool in algebra to deal with changing vectors. There's none. In order to deal with changing vectors, I kind of need some calculus stuff, right? Does that make sense? So in algebra physics class, everybody here is a constant. Everybody here doesn't change. Force doesn't change. Everything is kosher.
So if I just stand here and press on this wall and nothing's moving.
Absolutely no work is done.
Well, yeah.
Wait, so
Because nothing's changing.
I haven't accomplished
Now,
anything.
so
no, but if you spin it
what
in place,
what people think is because no work is done, it means that no change of energy happened. That's not necessarily true. That force did not get any work done. That force did not change the state of any system. Now, does that mean that other things in your system could have changed? For sure. If I go to the gym and I go to deadlift and I lift up the bar, while I am lifting, I'm doing work because the force that I'm applying on the system is getting it from the floor up. That's a change. If I just sit here and hold it, I'm still applying a force, but that force isn't getting any changes done. So that particular force isn't changing anything. It's not doing any work. Now, inside of my body is expending energy so that I can still do that force. Does that make sense? But that doesn't mean that that force is creating work. Somewhere else in the system, somewhere else in the big machine that is my body, energy is being changed. Is it at that force? No, that's not where it's being changed. It's being changed somewhere else. Does that make sense? What did you say?
When you said like inside my body, I'm exerting energy.
Energy is being changed.
Yeah, but then you're talking about two different systems. You're talking about the bar, now you're talking about.
If I make a system with the bar and me, inside of my body, the energy changes that are happening, for example, my muscles are changing probably some type of carb, whatever, into energy so they can continue to apply that force. That's not happening on the bar, right? That's not the force that is on the bar. That's a secondary, tertiary thing, whatever, that's happening because of the thing that I'm doing with the bar, but that's not changing anything with the bar. So if I think about the work done on the bar, none. There's no work done on the bar. Now, are there changes in energy, work done somewhere inside of my body? Yes. Will it be because of that force? Sure. Will it be from that force? No. That force will not be the thing that created the work in my body. Do you see what I'm saying? It's very specific. It's very nitpicky. It's a particular force that's producing a particular work. It goes kind of one to one. So if I sit there and I start pushing the wall, I could get tired very easily. And yeah, I probably changed a whole lot of energy. That force of me pushing the wall created no change, so that force did no work. Could other forces in my body do work? Yeah, sure. But that was not the question. The question was, did that force do work? And the answer is no. Just like if I take this thing and I hold it. I just hold it right here. Which way is the force? Up, right? If I push it up, then that force is creating a change. Does that make sense? Me holding it, right? That's why I'm trying to hold it flat. That force goes up. If I push it up, that force created a change. It only went up because I pushed it up. Does that make sense? Yeah. So that force did do work. If I hold it here and I move forward, which way am I pushing this thing? Up. I'm pushing it up. But that up force is not creating any changes in this thing up.
The work is zero.
So the work of that force up is zero. My up force.
It has to be in the direction of your force.
Some component of that force needs to go in the direction of that displacement. And we're going to talk about why in a second. Yeah. Let me go in order and then yeah.
Sorry, quick question. Okay, let's say you have that spinning chair, right?
Uh-huh.
Right now it's not spinning. I start to spin it, right? So it didn't move a distance, but it still has like acceleration. You said.
Then we're going to need to go into the rotational world, and it will move a rotational distance.
But you're not doing any like linear work. You're not doing any work.
No, but you could do rotational work.
Oh, you're still.
You
doing
could do that.
Okay.
Just twist your system. You could do that. That's totally fine. Gabby, what's up?
So in your example, when you're holding it up,
Mhm.
but not doing any work, could you still have energy?
Yeah, like I could still get tired, right?
No,
Some
I mean, sorry. Are you still exerting energy on the bar?
no, because I'm not changing the bar.
Okay, I'm just confused about the word ability for energy, the ability to do work. You could just drop it, and then that would cause.
See now, but if I drop it, is it my force that's getting that thing to fall?
No.
No, it would be gravity. So then in that case, would my force be the one doing work? No, it would be the force of gravity doing work. That's what I'm saying. It's very picky. It's very specific. It's a particular force doing a particular change. Okay? Yeah.
Just the second part of the second sentence, displacements can be along various paths between 2 points. Can you say that again?
So if I had like a path, I'm going to go back to the other side. But if I had a path that I wanted my object to
It
take.
doesn't have to be straight.
No, it could be any path. And in an algebra world, we deal with straight lines because it's way easier. But in a calculus world, we don't need to. We have the tools that will let us do this curvy linear stuff. We'll do a line integral, but a path integral, whatever. If I wanted to define a good equation for work, I would find the amount of force that I'm applying on an object and the tiniest bit of change that that force would create. Does that make sense? The tiniest bit of displacement that it would happen. And then I'm just going to keep adding that up. I'm going to cut it up into slices and then add all those slices together to get the total. Does that make sense? So that should lead you to believe that we're going to be taking integrals. When you take little tiny slices and you add them all up, that's an integral, right? Right? Makes sense? This right here, that right there, is not a regular multiplication. Turns out you cannot regular multiplication vectors. You can't. 3 times 5 is 15. Vector A times vector B, you can't do it like 3 times 5. It's not like scalar multiplication. But there are 2 ways that we can multiply vectors. The dot product and the cross product. One of them is called a scalar product, and the other one's called a vector product. Whatever. They're stupid names. But one of them is a dot. That's why it's a dot. Every math teacher I've ever done or ever had for calculus, when we do dot products, they actually draw the dot like a dot instead, like a circle instead of a dot because it's easier that way. But whatever. Now a dot product is weird. Do I actually go into the dot product? Yeah. Okay. So a dot product is a little bit weird because what a dot product does is it takes 2 vector quantities, right? And what it does is it finds the projection, or the shadow, of one vector on the other. How much does one vector go up the other vector? Does that make sense? How big is the shadow cast from one vector onto the other? So it's really talking about lengths. It's really talking about magnitudes. So a dot product takes 2 vector quantities, turns them into a scalar quantity. And that's why we use this for work, because work is a scalar quantity. So what we did here, we had a differential amount of work. In order to find the total amount of work, what we did is we summed up all of the individual pieces throughout the entire path, the entire motion of the object. And I'll get something that looks like the integral of f dot dr.
So we're not using the other one? Okay.
Well, yes, but yes, yeah. It depends on the problem. This, it happens again right here. It happens again in a second. But this is the algebraic workaround for dealing with dot products if we don't know calculus. We're going to get to that in 1 second. You don't have to write it just yet, but you can. We already talked about this. Whatever. Has anybody here actually, do you teach them the dot product? No? We're not going to actually do a whole lot of dot product-y things. What a dot product does, and I have examples of it actually written out step by step online that I will put up. But yeah, what a dot product does is it takes the components of the 2 vectors. So vector 1x, vector 2x, multiplies them together, and adds that to vector 1y times vector 2y, and adds that to vector 1z times vector 2z, and adds that together. It's the sum of the product of the components. There's an example online where I have this worked out 2 different ways, and it'll make more sense, but I just don't have the time right now to go through it. But you don't have to worry too much about the dot product yet, not really.
One more question. That integral, does it have limits of integration?
Well, the path AB, so from A to B.
What are...
So from this point A to that point B.
I understand, but what kind of values of those?
That's line integrals suck. And we're going to see an example for the line integral in a second. Usually what we're going to try to do for line integrals is define, if it's 2-dimensional space, we're going to try to define one variable like x in terms of y, so that we can then integrate from the bounds of y. Does that make sense?
Why do you keep calling it a line? It's not a line.
It's a path integral. That's really what it
That
is.
makes more sense.
But
People call it line integrals.
yes, because like a line doesn't have to be straight.
It does.
Not in non-Euclidean space. David did it. Noglied. Sorry.
Okay,
No, but like in calculus, a line.
so you're telling me that's a line in calculus? That curvy
In every calculus I've taken, they've always called it a line integral, but that's not necessarily. That's not a line. It's just a path.
Yeah.
It's just a path from A to B. It's a curvy line, man. It's a curvy line. If I have a constant force, then yeah, a force that doesn't change with time. It's just always a constant number. Yeah, if I have a constant force that's coming from a contact force, like I'm pushing something the same amount every time, then my work this is just the same definition that we had in the last slide of what work is, would turn into Nope.
Oh, you just made the dot.
Assuming 3D space. Assuming 3D space.
Why did you split the integral into each of the dot product?
Because dr, it could be a 3-dimensional vector of x, y, and z components. So then I could break this up as that's really what I'm doing there. And then since f is a constant, I can just multiply it in with the dot product on everybody.
Yeah.
So then this will turn into something that looks a little bit like that.
What's with the x hat?
They're the unit vectors, remember, that go in the x direction, the y direction, and the z direction. So this is vector form for something that has x components, y components, and z components.
But you don't have to write it in that first one.
I'm already kind of implying it with x, y, and z.
Which contains the
Kind of. I'm just being really picky here, telling you this goes in the x, this goes in the y, and this goes in the z. I should write it there, but I'm trying to save space.
The force being constant contributes what to that? Like, what would you not be allowed to do there if it wasn't constant?
I would have to then break, we're going to actually do that as an example in a little bit, but I would have to find the components of this in the x, y, and z, and then I would only be able to distribute the x component into the x component of dr, the y component of f into the y component of dr, and the z component of f into the z component of dr. And what I can do here is just factor the f out entirely, because it's constant for everybody. So what this is going to end up giving me if I factor out the f because it's constant and it doesn't change, what this is going to end up giving me, I'm not going to skip steps actually. Is something that looks kind of like that.
And how'd you get that?
Well, if I integrate drx between x initial and x final, that's going to give me x evaluated between final and initial. So that's final minus initial. So what I'm going to end up getting is force times delta x in the x, plus force times delta y in the y, plus force times delta z in the z, depending on what components I have. I don't believe we'll ever see anything 3D. I asked and they said no. So, but they also said that there's a ton of calculus, and then every teacher says there's no calculus. So I don't know who to believe anymore. But I just want to keep it as general as possible. Okay. So when I do the integral thing, what I'm gonna end up getting is something that looks very similar to force times displacement. Very, very similar, right? With some stuff, plus force times displacement in the other dimensions. Gabby, what's up?
If you have a 2D vector for position, can you just do Pythagorean and to do dot product?
No, because.
Just to find the magnitude of the.
But the thing is that you're not taking that hypotenuse path.
Oh.
The important part is that you are applying this force over the path that this thing is moving. Just because it's got x and y components doesn't necessarily mean that it's going to move in that hypotenuse motion, right?
How do you plug it back into your equation? Like you have some curvy thingy. How do you make it go into your equation? I don't get that. Like, how does
That will be what these values, that curvy thingy is going to have changes in the values. If it's a two-dimensional curve, it'll have changes in its values in the horizontal, which would go here.
But you're only giving final and initial.
Indeed. So we care, when we have this constant force and we're doing work, we really care about the beginning and end points. Because we really care about those beginning and end points. Now, we could work around doing all of this work. We can get around some of this stuff by taking that second definition that they gave us 2 slides ago for the dot product and using the magnitude of f times and to be fair, very often actually you'll see this as d instead of delta x. D makes me feel weird because delta x is displacement. So whatever. But they mean the same thing in other sources. So if you take the magnitude of f times the magnitude of displacement times the cosine of, often you'll see that as theta. I don't want to write it as theta because we use theta to describe where a vector is starting from where?
Origin.
No, you can't start an angle from a point.
Not the origin. That's from
The x-axis. Starting from the x-axis. That's what we've always taken theta to be by convention. Now, that is not what that angle represents. That angle very specifically represents the angle between the 2 vectors. It's not the angle between the vectors and an axis. It is specifically the angle between the 2 vectors that you're taking the dot product of. And that is probably the number one place that people mess up when it comes to finding work. Because they'll give you problems and they'll give you an angle and they'll say, hey, here's a vector at this angle. Here's another vector at the same angle. Find me the work. And people will use the angle given to you as phi, as the angle between the 2 vectors. It doesn't have to be. What does that look like? If I told you vector A is 5 units long, makes an angle of 20 degrees relative to the positive x, you should all think of a vector in the first quadrant that makes an angle of 20 degrees right here, 5 units. Okay. If I said I have a second vector, vector B, that makes it's 3 units, and it makes an angle of 10 degrees relative to the positive y, then we should have an angle or a vector that goes in the second quadrant, starts here, 10 degrees. Neither of those two angles is phi. The angle phi would go from the first vector to the second vector. It would be that. And we would need to use a little bit of geometry to figure out what that angle is. It shouldn't be very hard, 80, right? It shouldn't be. But the point that I'm making is that sometimes they will give you an angle and you might not have the angle you think you have. What happens if they told you that angle B, or vector B, is on the x-axis?
So then you can't do it.
At that point, the angle that they gave you happens to also be the angle between the vectors. Does that always happen? No. Is that a definition? No. How do we fix that? We draw the picture. The picture will set you free. If you draw the right one. If you don't, then, I mean, you tried. Better luck next year, but yes.
So when will this algebraic trick not be applicable?
If they gave you a displacement vector in vector notation with x components and y components split up, it's not worth the hassle. It isn't. You're better off doing the integral and the dot product.
Same thing,
Kind of.
doing it in a different component.
Yeah. You're better off doing it the calculus way than the algebra way if you've already got it in vector form. If you don't, because this method only works with the magnitude of the vectors. If I have to go through a whole lot of rigmarole to find the magnitude of the vectors, it's not worth it. It just isn't. I'd rather just do the calculus. But if you already gave me the magnitude of the vectors, then yeah, I'm just going to do this. Because the alternative would be to find the components using sine and cosine, put it into vector form, and then do the calculus. It's just not worth it. It really isn't. I think we're done, right? All right, so to look at, we'll start here next time. There will be a homework up. There will be.
I don't know if this is a dumb question, but how can displacement not be
What's up?
If I got anything less than a
curvy?
102,
In what? Computer science?
I would be very disappointed.
I'll be so disappointed.
anything less than a 102,
Literally so disappointed.
unless you screw this over by getting this wrong.
That's your distance. Wouldn't your displacement just be b
Well,
minus
your
a?
displacement vector would be the vector that points in the direction that you are moving at any given moment. And that's actually why, if you look at what we use to define it, we used dr, the differential displacement vector. It's not just r, because r would go from here to here, and it would point that way always. dr would point in differential distances. dr at this point would
So
point
how
that
can you
way,
pick
and
just
here.
one x component?
You're not. What you're really doing is you're adding up all of them. Blam, blam, blam. All of them all together. All the way up. That's why you have an integral.
Right.
So that you get the total net.
Okay,
That's what
fine.
you're doing.
Okay. That makes sense. Thank you.
And then what you'll end up with is that delta x and delta. Because as I add them all up, what it's going to turn into is just a vector that points that way. That's what it's going to turn into.
Okay.
Now, when does that change? What happens if f is not constant? Then that thing is going to change. And that's going to be like 5 slides from now.
You could do what I told you, like Pythagorean, if you know for sure
That
your
you're moving
displacement
along the-
is.
That as long as you're moving in a straight line, yeah.
Okay.
But
Yeah,
I mean, well, why?
Would you be willing
Hey,
to
Emily.
look up the midterm for me, or I'm gonna email you.
Could, yeah, just please email me so I can have lunch.
Okay.
That would be great.
I understand. Yeah, I'll email you.
What did we get to? We got to page. What's up?
No, I can't come after
12.
school on Monday, so it was the same question. Should we
I,
email you?
I'll email you if you want to go over it, then we'll just figure out a time that you're free, and then I'll accept Tuesdays because we have our meetings. Bye, Gabby. But yeah, I'll the grade I have no problem telling you over email apparently. What page is this? Oh my God. I think it's 1 through 12. Is that what it was? But if you want to go over each question individually, we can just set up a time that you're free, and then we'll do that.
Thank you.
No problem. Oh, haha, it is 12. Huh?
Cold today.
Everybody seems to be cold today.
Like Antigua was Target. And it's weird because it came 20 degrees, but I was dressed.
Huh?
How's your foot?
It's okay. It's got its moments. Sometimes it's really good, and other times it's not so
You
good.
ready to fight? Or?
No, I looked at the weather today, and it said that it was gonna rain, and I was like, nah, I'm not about to get wet. I'm not in the mood to get wet. I've been in a really crappy mood all day, so. So I came in the car. But yeah, I'd rather actually be on the bike than the car, because on the bike I don't need that foot. Today is the 8th. Okay. Here we go. Putting up the PowerPoint. Oh, I did not turn off this video.